This is one of those occasions where you come up with a title and then you work backwards to figure out what the talk was. So 4GL's been a word that's been lodged in my head for a little while. It was really when we pivoted to being a SQL database. I started researching everything I could about how people view SQL, and this word 4GL came up quite a few times. So I want to sort of explain what that means. But in its essence, it's this idea of how we can program without programming. Like how do we take all the work out, just have the fun bits, and sort of make the computer as smart as possible? And like a nice crisp definition or way of thinking about this is to be declarative. You say what you want, and the computer goes off and figures it out. It searches the space of ways to fulfill the thing you need. And every generation has this dream, and as I'll go through sort of a bit of a history, everyone wants to achieve this, and over the years, the manifestation of this changes, and the definitions keep receding away from us. The more clever our systems get, the more we say, well, that's not AI. It needs to be able to do this, this, and this. But this core idea has stayed throughout. But there is a corollary, which is that in order to achieve that, to be declarative, it's almost useless if you can't verify what the output is. So in order to be a useful declarative system, you need to be able to quickly say, yep, that looks good, or evaluate that somehow. So this is a recurring tension, this idea of a verification cost, and we're going to take a look at the history of this. So I don't know if anyone in the room would recognize this man off the face. I'm curious, does anyone know this gentleman? Do you recognize the face? Okay, so this man is JCR Licklider. If you've ever watched an Alan Kay talk, he talks about Lick all the time. This is Licklider. I actually bought a biography of his called The Dream Machine last year, and I've been slowly working my way through it. It's very dense. The print is very small. So I'm about 3 chapters in, but it's really interesting. It goes all the way back to the beginning of the 20th century and the dawn of electronic computing. But in 1960, Lick came up with this paper called Man-Computer Symbiosis. And in that he writes, men will set the goals, formulate the hypotheses, determine the criteria, and perform the evaluations. Computing will do the routinizable work. Now, Licklider wasn't a language designer, or he wasn't designing programming languages. He was looking at this from a psychologist lens, as from the human side. And he, I think, articulated here a vision which would extend not just to personal computing, but to all of computing. But crucially, Licklider worked at the Pentagon, and he funded the development of the ARPANET, which became the internet. And he also inspired and worked with people like Bob Taylor, who led Xerox PARC, and funded them to build personal computing out. So he's like a really pivotal person in computing history. So I'll tell you more next year when I've finished reading the biography. But what Lick is essentially describing is 3 steps, and I didn't conspire with Henry to, I had no idea Henry was going to talk about or mention the word verification or search, but it's essentially this, right? You declare something, the computer does all the searching, and then the human or someone verifies the output. And that's the essence of what Lick was describing. So in the beginning, the first compiler, written by Grace Hopper back in 1952, all it did was link. It was linking machine code, very, very simple. You wouldn't even describe this as a programming language nowadays, but we describe it here as a first-generation language. So yeah, she was working on a machine called the UNIVAC, and she had this radical idea that maybe she didn't just have to write out the machine code in the most dumb possible way. She could use the machine to then organize the layout of the code a bit. She believed that English could be used to program computers. In 1953, so just a couple of years later, John Backus, whose name possibly rings a few more bells, was working at IBM, and he suggested to a colleague, I keep having this idea of automatic programming or automatic coding. And by 1957, this became Fortran, running on the IBM 704, which was state-of-the-art commercial hardware with 144K of memory and could run about 40,000 instructions a second. And so there was this jump where from the first generation, you then had assembly, which was the second generation language, and Fortran was really the first third generation language. A year later, we had Lisp. So John McCarthy came up with a completely different kind of third generation language in 1958. But actually, so I should go back and just say John Backus then in 1977 wrote this Turing Award lecture where he actually says, maybe Fortran wasn't such a good idea, and we should probably all be doing functional programming instead, which is kind of the same ideas that John McCarthy embraced or sort of saw with Lisp, and he reflected on Lisp, saying actually maybe Lisp's sequential processing of programs as Lisp is actually, it's not completely without flaws, right? It has disadvantages, as he says here. And then shortly after this, there's another language you've probably heard of, and you probably, if you're not a Lisp programmer or you haven't ever looked at Fortran in any depth, they all sound the same, and this one is COBOL. And COBOL was trying to do something a bit different. Unlike the other two, COBOL was written with the persona in mind that a business user could actually type into the computer and just control and declare what should happen in the program. And this never really succeeded. And there are various reasons for that, but essentially it's a very hard problem, right? They were trying to push above this third generation language and achieve something which was more declarative. And because of this, it was too early. The ideas were too coupled to the mainframe architectures of the day. It never really succeeded. COBOL's still running in places in the world all this time later, but it's generally derided as not a good successor to 3GL languages. But then a few years passed, and finally we had something which we could all call fourth generation language. And this started with the relational model released in 1970, or documented in 1970, and then became SQL a few years later. And SQL, some would say, is the greatest fourth generation language that exists. It's the one that people actually think it's all right. It's still in use today. Lots of databases are built around SQL. You describe the data you want using the query. The query engine takes that query, parses it, compiles it, runs all kinds of optimizations over it, turns it into an execution plan, and sets off to find all that data you're trying to look for amongst many different hard drives, many different machines, potentially over different data centers in the world. And then finally, it brings all that data back, and you as the end user can say, yep, that looks good, and you can quickly verify that result. It's a very, very productive language, and there's a reason why 50 years on, everyone is still talking about SQL. There was another language a couple of years later after that relational model paper was written called Prolog. If you've not looked at Prolog, it's quite interesting. But it is an also-ran system. It's not generally used in industry. It does have some niches where logic programming and constraints are really important, where it has had some success. But it's built around the same kind of ideas as SQL and the relational model. But it wasn't focused on data access and retrieval. It was purely looking at logic and rules. It's actually quite good for things like program analysis, and you may have heard of Datalog, which we dabbled with a bit. But that is sort of looking at the essence of Prolog and making it apply to data access. But the key ideas is Prolog is unification and backtracking. So these are different kinds of search approaches which make the computer more intelligent. It means you don't have to decide the ordering of operations in a program. But it really is a footnote in the history of things, which is a bit unfortunate because I think that has some fantastic ideas. And then a few years later, the word 4GL finally gets coined, because up to this point, everyone's just scrambling around looking for something to replace these third generation languages, which force everyone to have to think about sequentiality of programs. So James Martin crisply defines in this book from 1981 with an explicit promise that business users should be able to write their own apps. Sounds familiar? I think we've been iterating on this idea for a while. And there were various things at the time, products that came about around this. So you could have report generation and what we call case tools to look at use cases, essentially, and define how software should be built, and then generate the UIs from the definitions. But of course, there's one instantiation of this which everyone will know very viscerally, which is spreadsheets. So this is VisiCalc running on the original Apple II, and this actually really made the Apple II sell. Like Apple, I don't think would exist in its current form without VisiCalc being one of those sort of killer apps that drove people to pick up the Apple II. And VisiCalc was invented by one guy, Dan Bricklin, who just sort of came up with this idea of having like a grid layout, and you create formulas, and the computer searches that dependency graph, reruns the calculations, and you as the end user, you get something out of that. You haven't had to say, I want to run this cell, then this cell, then this cell. The computer's doing all that work to figure out what to do. And this is arguably also a very successful 4GL. I don't think it has the same feel-good factor as SQL, though, because everyone's trying to get rid of spreadsheets. If you're working in a bank today, you don't really want spreadsheets around. They hit a complexity ceiling. And let's talk about that. So what is the problem with spreadsheets? Well, it's that if you want to use a spreadsheet well, you still have to think like a programmer. And Fred Brooks describes this in the No Silver Bullet, that software is composed of essential complexity and the other one, incidental complexity. So read my notes. Accidental complexity is, you can get rid of that, and that's what 4GLs are quite good at. But most problems that people actually want to still are actually still very complicated, and you still have to think like a programmer to solve them, so that they're sort of irreducible in the complexity. And so if you can't reduce that irreducible complexity, then the 4GLs really pay their way in every circumstance. And I guess with spreadsheets, you find that a novice person can store a little bit of data, but as soon as those spreadsheets grow and grow and grow, you basically have a very poor man's database, in which case SQL. So what can we do about this? What can 4GLs do to solve this? And I think we're at this really interesting point where there are some new ideas coming in. So if people haven't seen Andrej Karpathy's talk from the summer, I caught it and I was like, yeah, that's a really nice articulation of the relevance of LLMs. And if you don't know Andrej, he co-founded OpenAI, and in this keynote talk, he describes how everything we've just been talking about is software 1.0, where you write the language, you tap it into a keyboard, press run, and it does a thing. And he says software 2.0 is this idea of training neural networks in general. So maybe you have some data, you put it through some statistical algorithm, you come up with maybe a neural network or other kind of statistical structure, and it does some useful work, right? That's software 2.0. And then he says, but we're now in this age of software 3.0, where neural networks themselves have become programmable, and the thing that we're using to program them is English. Okay, so this is literally an instantiation of that 4GL dream again, except we have these natural language prompts, we have sampling, or the machinery running on GPUs, it's all figured out, but the crucial step is the verification. So we don't have a clear, solved, how do we verify the outputs of LLMs? And this means they're not actually that good as a 4GL in themselves, right? Because they're kind of useless. Business people don't want to create broken software. So that question mark at the end is the solved problem. And Karpathy acknowledges this himself. He says, the more a task is verifiable, the more amenable it is to automation. Tasks that are verifiable progress rapidly, while others lag. So, he acknowledges that without verification, this stuff is questionably useful. But crucially, this idea of the 4GLs, and it's not just about business users, it does actually go all the way down the stack. And so if you look at within, say, the GPUs that are running these machine learning algorithms, they're very complex multi-core processes. They have all these scheduling problems, and to determine the optimal scheduling and the tiling of the data and the layout is like a really difficult problem. And what you end up doing is essentially a search algorithm, and the design of those, the software for that, but also the design of the hardware for those systems is all being done using these declarative algorithmic approaches. And the only way you can verify any of this stuff is to benchmark it. Is it faster? So up and down the stack, we're sort of using these same approaches: declare, search, and verify. And in databases, we have other things that, or other areas where these steps apply. So we have learned indexes, we have compression methods where it learns the shape of the data and then does the compression, because you can get orders of magnitude more compression performance. My own interest in databases is certainly around this XTDB product we've been building. And one articulation of this is from this paper from 1977 by Ben Michael Schuler, where he really crisply articulates the reason why managing errors and obsolescence of data is like a hard problem that SQL itself doesn't solve, right? So he's saying in 1977, 3 years after it's come out, yeah, SQL has these flaws because it doesn't account for errors. So it makes it hard to verify things. And it's been many years since, and what we're working on in XTDB is like, how can we make SQL a better language for establishing what errors are and doing verification. And yes, so databases can help us figure out ground models of truth that when we get LLM output, we can then say, well, is that actually true based on the business data? And this is like a really important connection. So the actual sort of mainstream way of articulating this is neurosymbolic architectures, which I don't profess to be like an expert on, but it's essentially the idea of you have this fuzzy, messy world algorithms, and then you have statistical systems. Then you have the rigid, it works every time sort of software approach. And the question is, how do you glue these things together? How do you build useful systems that can combine both? And this takes us all the way back to Licklider's man-computer symbiosis, right? He was thinking about humans and machines, whereas we're talking about machines that behave and think a little bit like humans, obviously not anywhere near as well as humans do, but how we do sort of computer and computer symbiosis, where one of them is like this fuzzy organic sort of feeling thing. So the 4GL dream isn't wrong. I think it's just asymptotic, and the more every generation of developers approach it, the more we realize we're sort of just trying to solve the same problems over and over again, which is how do we improve the declarative description of languages? How do we make better search algorithms to search the space as quickly as possible? But then crucially, how do we verify? So the future isn't no programming, it's programming at every level, but with verification at every level as cheaply as possible. So yeah, I think Licklider's crisp definition of how personal computing should work really applies to the world of AI today, and I think it's worth learning a bit about. So anyway, that's a little bit of a tour of some history. I hope that was interesting. Thank you.